Hey everyone, and welcome back to the channel. Today, we're embarking on a fascinating journey into the world of recurrent neural networks, or RNNs. These clever networks are specifically designed to tackle data that unfolds over time, like the words in a sentence or the fluctuations in a stock price. Now, what truly sets RNNs apart from the more traditional neural networks you might be familiar with? It all boils down to memory. Unlike standard networks that treat each input independently, RNNs possess a remarkable ability to remember information from previous steps in the sequence. This memory allows them to understand context and relationships within the data over time. Let's think about a real world scenario. Reading a sentence. When you encounter the phrase, the cat sat on the, your brain doesn't process each word in isolation. Instead, you remember the preceding words, the and cat and sat, to help you predict what might come next, like mat or fence. RMNs operate on the same principle. They maintain an internal memory of the sequence they've processed so far, using that context to make more informed predictions and decisions. At the heart of every RNN lies the recurrent neuron. Unlike the static neurons in feed-forward networks, these neurons possess a crucial feature, the hidden state. Think of the hidden state as the neuron's memory. It holds information about the previous inputs in the sequence. To better understand how this memory flows, we can imagine unfolding the RNN through time. This essentially shows us the sequence of operations the RNN performs, step by step, with the hidden state carrying information from one step to the next. Now, let's look at the architecture. A key difference between RNNs and other deep learning networks is that RNNs share the same set of weights across all time steps. In a regular neural network, each layer has its own unique set of weights, but in an RNN, the same weight matrices are applied repeatedly as the sequence is processed. This weight sharing is what allows the RNN to learn generalizable patterns across different positions in a sequence and effectively remember information over time. So, how does this process actually work? At each time step, the RNN takes in the current input and combines it with its hidden state, which, as we know, is its memory from the previous step. This combined information is then processed to produce two things: a new hidden state, which carries forward the updated memory, and an output for the current time step. This process repeats for every element in the sequence. The network learns through a method called backpropagation through time, where it adjusts its weights based on the errors it makes at each step in the sequence. RNNs aren't a one-size-fits-all solution. Depending on the nature of the input and output, we have different types of RNN architectures. The one-to-one is essentially your classic feed-forward network. Then we have many-to-one, where a single input generates a sequence, like creating a caption for an image. Many-to-one takes a sequence and produces a single output, perfect for tasks like analyzing the sentiment of a text. And finally, many-to-many deals with sequence-to-sequence tasks, such as translating languages. Beyond these basic types, we also have more advanced variants like LSTMs and GRUs, which we'll touch on next. While the basic vanilla RNN is a great starting point, we also have specialized variants designed to address specific challenges. Bidirectional RNNs enhance context understanding by processing the sequence in both forward and backward directions. For handling very long sequences and the issue of vanishing gradients, we have powerful models like long-term storage memory networks, LSTMs, and gated recurrent units, GRUs. These architectures incorporate gating mechanisms that allow them to selectively remember and forget information over extended periods. RNNs bring a lot to the table. Their ability to process sequences and understand context makes them incredibly valuable. Plus, weight sharing allows for efficient learning. However, they also come with certain limitations. Training deep RNNs, especially on very long sequences, can be challenging due to issues like vanishing or exploding gradients. This can hinder their ability to learn long-range dependencies. Additionally, training complex RNNs can be computationally intensive. Despite their challenges, RNNs have found tremendous success in a wide range of real-world applications. In time series prediction, they can forecast future trends based on past data. Natural language processing heavily relies on RNNs for tasks like machine translation, text generation, and understanding the meaning of text. Speech recognition, powering our virtual assistants, also utilizes RNNs. And even in video analysis, RNNs can be used to understand sequences of frames and recognize actions. So, to wrap things up, recurrent neural networks are a powerful class of neural networks that bring the crucial element of memory to deep learning, enabling us to process and understand sequential data. They make context matter. If you enjoyed this breakdown and learned something new, please give this video a thumbs up and subscribe to the channel for more deep learning explorations. Let me know in the comments which application of RNNs you find most interesting, or if you have any questions. And definitely let me know in the poll if you'd like to see a practical coding demo in our next video. Thanks for watching, and I'll see you in the next one.